Okay.
Here we go.
Newton's third law. For every action, there is an opposite and equal reaction. You must be aware that it's opposite and that it's equal. So same number, different sign. This is known as an action-reaction pair. And it has to act on different objects. Let me show you something very, very deep. You can't touch without being touched. Poof.
That's
I
all
know,
there is
right?
to it.
Now it'll haunt you the rest of your life. Mathematical representation or rule. This is a pretty useless rule. It's not really useful, but the idea is there. So given two objects, let's say we have object 1 and we have object 2, then the force of object 1 on object 2 is equal to the same force of object 2 onto object 1, but opposite. In other words, you get that opposite and equal reaction. Okay, so it's the same force, but it's going to have a different sign. This one was positive, this one was negative. Not useful at all. You'll never plug numbers in. It's just ridiculous. This is Newton's third law is a lot more heavy conceptual, and it's definitely more of the backup. So it tends to be useful, especially with Newton's first law, and that's why I'm going in this order. A 10 Newton force and a 50 Newton force are acting from a single point in opposite direction. An object, right? I have a 10 Newton force going this way, and I have a 15 Newton force going this way. I'm going to draw a little longer. What additional force must I add to keep everything balanced in equilibrium? What must I do to keep this in first law? Well, you'll notice that if this is 15 going this way and 10 going this way, I'd have to go ahead and add 5 more in this direction, right? So I would add 5 newtons more of force in the direction of the 10 Newton force. Okay, don't say left and right. Keep him, because I could have drawn this the other way. You would answer correctly that you would need 5 newtons in the direction of the 10 Newton force. Now, what this does to us is if we go ahead and do that, you'll notice that this is 15 and this is 15. So essentially, this is Newton's third law because they're opposite and equal reactions. So all the problems we did on Newton's first law, lecture note, those are technically opposite and equal reactions. They were keeping things in balance. Except one is going positive, right, and one is going negative. Here's the one that people always goof up on. According to Newton's third law, it would have to be an opposite and equal reaction. I remember the first time my college professor taught me about Newton's third law. I I thought that he was on something, right? Because he went ahead and said, "All right, guys, I'm pushing on the wall, and guess what? The wall's pushing back." And we were like, "What is he talking about?" Well, think about it. If you push on a wall and it doesn't fall over like a domino, guess what? The wall must be pushing back with the same force. Okay. It isn't until you go ahead and push with a greater force and everything becomes unbalanced that things begin to move. So consider for a moment, if you push anything and it doesn't budge, it's because it's pushing back at you with an opposite and equal force. So for the soccer ball, if the foot hits the soccer ball with 50 newtons of force, guess what? The soccer ball hits the player's foot back with a force of 50 newtons. It would be negative because it's in the opposite direction. Okay, you know that sometimes if you ever kick the soccer ball wrong, okay, maybe just head on with toes, and you didn't have good shoes, you felt it. You felt it. Okay, yeah, the ball went, but your toes felt it as well. Problem 2, slaps roof of car. Car slaps Isaac Newton back. Take a moment to explain this meme in the context of Newton's third law.
Most impressive.
Problem 3, here are some interesting pairs, action-reaction pairs. So in the first case, you'll notice that the ball is hitting the player's face. Now you know that noses don't do that, or faces for that matter, or skulls for that matter, right? But you also notice that soccer balls don't look like that. So what's happening is Newton's third law, okay? The ball is deforming because the ball is hitting the face, but the face is hitting the ball. Okay, so when the face hits the ball, the face deforms the ball. When the ball hits the face deforms. They're both deforming each other. Okay, and this is not a Photoshop picture. I'm going to show you a video, and you're going to be like, "What the heck?" It's physics. It's reality. Okay, so the action reaction pair here is the ball and the face, right? The ball hits the face hits the ball. Boom, third law. Okay, baseball. You know, baseball doesn't look like that, and you're thinking, okay, the soccer ball makes sense because it's full of air, right? But you know, a baseball is filled with more than just air. It's not even filled with air, really. Okay. It's a composite material because it has different layers of different materials for different purposes. Okay. Some of it is to add density, some of it is to add weight, some of it's to help with what we call rotational inertia. Okay. That allows you to go ahead and do cool tricks when you pitch. Okay, like curve balls and things like that. The action reaction pair here is that the ball hits the bat and the bat hits the ball. Obviously, the bat deforms the ball. But a bigger question is, does the ball deform the bat?
A baseball bat is one tough item, but how tough? What really happens when bat meets ball? And why does the bat sometimes break? Even the Time Warp Lab has its limitations, so we decided to pay a house call to another lab.
This is the only place in the country where you certify the bats and the baseballs in the major leagues.
Welcome to the University of Massachusetts Lowell Baseball Research Center. Here, Patrick Drain will show Jeff and Matt the scientific reason for broken bats. And to do so, Patrick uses this crazy machine.
What we basically have here is we have a bat hanging here vertically. We're going to fire with an air cannon a ball at 160, 180 miles per hour and see what the collision looks like and go from there.
We're loading the machine with a regulation wooden bat made of ash, a longtime favorite in the big leagues.
That's way too fast to see.
Now to whip some ash, Time Warp style.
Okay, that's good for focus.
We're all set to fire. Are you ready?
I'm all set up. Okay.
At 10,000 frames per second, we can see that regulation hardballs turn into squash balls when they hit the bat.
And right here, you can see the ball is actually starting to wrinkle.
Right, it has to go somewhere. That, to me, looks like a fake baseball.
Yeah, that's a real Major League Baseball.
If I just saw a frozen frame of that, I would think that you really destroyed this ball. This is about a third of the ball compressing almost flat. That would take, 50 or 60 of me standing on top of one of these to make it compress like that.
Or a couple cars.
Or, we hasten to add, a professional ball player. So the ball's not even as tough as we thought. But that just makes the sight of a splintered bat all the more mysterious. What gives? Clearly the ball, but what else?
So in this shot, we see the full bat.
And the bat bends too?
This makes me feel like every single piece of equipment in baseball is made out of rubber. It's totally unexpected because we look at a bat like this and it feels totally solid.
With this last picture, we have the hammer and the nail. Okay. As long as this is balanced, the nail won't drive in. Okay. You may have the hammer may hit the nail, but if the nail is not going in, that means that the nail is hitting the hammer back with the same force. That is an opposite and equal reaction. Okay. It's only when the hammer exerts a greater force, that would be Newton's second law, that's when the nail begins to drive into the piece of wood. Okay, so the action reaction pair here is the nail hits the hammer or the hammer hits the nail. For your summary, explain what the earth must be doing to your body according to Newton's third law.